Alright everybody, in today's video we're going to be looking at section 8.1, dealing with non-right triangles, specifically what's called the law of sines in section 8.1. And we want to think of the law of sines as basically a tool to help us solve triangles. Again, solving triangles means you want to figure out the missing angles or the lengths of the missing sides of the triangle, given some information about the triangle. And what's specific about the use of the law of sines is you would use it when your triangle is not a right triangle. So we use the law of sines to solve non-right triangles. If the triangle is a right triangle, you don't need the law of sines. You use basic right triangle trigonometry to solve it. But we're trying to solve triangles that have generally a look like this to them. So you're going to have three sides, A, B, and C, and you're going to have three angles. Now the angle opposite of each side, instead of using the Roman letter, we're going to use the Greek letter. So across from side A will be Greek letter alpha. Across from side B will be Greek letter beta. And across from side C will be Greek letter gamma. That's the A, B, and C of the Greek alphabet. Alright, now the reason the law of sines is called the law of sines is it simply says that the ratio of the sine of an angle versus the side opposite that angle holds constant for any of the three pairs that you could create for this triangle. In other words, the sine of angle alpha, when divided by the side opposite it, is the same as the sine of angle beta divided by the side opposite it, which is the same as the sine of angle gamma divided by the side opposite of it. Now it's easy to remember that this involves sines because after all it's called the law of sines. So what you really need to focus on simply is the idea that it's an angle-side pair that go into this ratio, an angle and the side opposite it. And it really doesn't matter whether you think about the law of sines this way, or if you flip all of these. You could write it as side A divided by sine of angle alpha is side B divided by sine of angle beta, there we go, is equal to side C divided by sine of angle gamma. That's an equivalent expression. It doesn't matter which way you think about it. Okay? So it's very, very easy to remember the law of sines. And as you'll see in some of these exercises, it's also pretty easy to apply it. So let's take a look at solving a triangle. This is problem number let's see, problem number 10 in our exercises, where the information they give us is that side B has a length of 10, and we don't bother with units. It could be 10 inches, 10 feet, 10 meters, it doesn't matter. Angle beta is 95 degrees, and angle gamma is 30 degrees. All right, my goal is to solve this triangle, meaning I have to find the two missing sides. So I have to find the length of side A, and I have to find the length of side C to this triangle. And I have to find the one missing angle. Well, I've got beta and gamma. I have to find angle alpha. Okay. All right, now what clues me in that I should use the law of sines is because I have a side angle pair. The B and the beta go together. And when I have a side angle pair, that's the ideal setup to apply the law of sines. Because according to the law of sines, it's the sine of this angle divided by this side, the sine of 95 degrees, divided by 10, that can be compared to any other side angle pair I choose. The pair I'm going to choose is the angle gamma involved. So that's the sine of 30 degrees divided by the side opposite of gamma, which is side C. And what we see here is a very simple equation that I can solve for side C. If I multiply 10 times both sides and C times both sides, I get C times the sine of 95 degrees is 10 times the sine of 30 degrees. Then divide both sides by the sine of 95 degrees. And we have solved for C. So this becomes a calculator exercise. On my calculator, 10 times the sine of 30 degrees divided by the sine of 95 degrees. And I get 5.019 and on and on. Okay. In this exercise, they ask us to round our answer to the nearest tenth. So to the nearest tenth would be the 1 decimal place. That's going to be rounded to 5.0. I'm sorry, C is right here. 5.0 is that side, okay? All right, now I still have to find side A and angle alpha. What I'm going to do here is realize this. They've given me 2 of the angles within this triangle. The sum of all 3 angles within any triangle always has to add up to 180 degrees. So I can find angle alpha simply by saying 180 degrees minus the 2 angles I know. So on my calculator, 180 degrees minus 95 degrees and minus 30 degrees, and I get angle alpha is 55 degrees. Now, once I know angle alpha, I can go after side A. Go back again to the original side angle pair you were told. The sine of 95 degrees divided by 10, and compare that to the A and the alpha. Okay, the sine of 55 degrees divided by side A. And just like above, we can solve for A here. You multiply both sides by 10A. That gives you A times the sine of 95 degrees is 10 times the sine of 55 degrees. And you divide both sides by the sine of 95 degrees. And on your calculator, you get your answer. So 10 times the sine of 55 degrees divided by the sine of 95 degrees, and I get 8.2228. And again, we're rounding to the nearest tenth, to the nearest 1/10 would be to the nearest first decimal place. That's 8.2. And I'm done with the problem. We have solved the triangle. Okay. All right, let's try a second example. We'll flip this over and conserve a little paper. Let's go ahead and solve problem number 14. In problem 14, we're told that angle alpha is 119 degrees. Side A has a length of 14, and side B has a length of 26. And the prompt here says, of course, assume angle alpha is opposite side A, beta is opposite side B, and angle gamma is opposite side C. And then from this information you're given in the problem, determine whether there's no triangle, 1 triangle, or 2 triangles that are solutions. And of course solve. So we simply go about the process of trying to solve this. The side angle pair that I know is A and alpha. That's how I start the problem. The sine of angle alpha, sine of 119 degrees, divided by side A, can be compared to another side angle pair. In this case, I'm going to compare it to the B and the beta, because I know the B. The sine of angle beta over the length of B. And so, of course, you're going to solve this for sine of beta by multiplying both sides by 26. So 26 times the sine of 119 degrees divided by 14 is going to be the sine of beta. And let's work that out on our calculator to see what we get. 26 times the sine of 119 degrees divided by 14, and I get 1.624. So now I'm going to try to solve for beta. Sine of beta is 1.624. I will use the inverse sine function on my calculator. And see what happens when we do this. The inverse sine of 1.624. When I hit that, I get domain error, of course. That is because you cannot take the inverse sine of a number that's not within the interval from -1 to 1. In other words, the sine of beta never gets to be as big as 1.624. That sine wave is trapped between heights of -1 and 1, right? It never reaches a height of 1.624. It's trapped in height between -1 and 1. So there is no solution for beta. And what that simply means is there is no triangle where you could have an angle alpha of 119 degrees, a side A of length 14, and a side B of length 26. That's a physical impossibility to have. Okay? All right, let's take a look at problem number 20. In 20, they tell us that side A has a length of 7, side B has a length of 3, and angle beta is 24 degrees. The side angle pair I have is B and beta. That's how I start the problem. The sine of 24 degrees over 3. What I want to compare that to is the A and the alpha, because I know the A. The sine of alpha over 7. Multiplying both sides by 7 to get the sine of alpha by itself, I get 7 times the sine of 24 degrees over 3. Let's see what that is. 7 sine of 24 degrees divided by 3, and I get, oops, I think I have to redo this. 7 times the sine of 24 degrees divided by 3, and I get 0.9491. Now that is within the interval from -1 to 1. So when I hit inverse sine of 0.9491, I will get an alpha. Inverse sine of 0.9491 gives me 71.6 degrees. Okay, so we have solved for alpha. Now the question is, since I hit inverse sine to solve, is there a second solution? So just like we did in section 7.5, you have to flip that angle to look for a second solution. Remember, inverse sine only sees the right half plane. So it was able to find this 71.6 degrees. But what it can't see is what an angle over here would be as a solution. That's going to be 180 degrees minus 71.6 degrees. And we get 108.4 degrees. There's a second solution for alpha. Okay? Now, they told you beta. You just found alpha, 2 versions of it. You can now find gamma, can't you? Beta is 24 degrees. If alpha is the 71.6 degrees, then gamma is going to be 180 degrees minus the 24 degrees and minus the 71.6 degrees, giving me 84.4 degrees. On the other hand, using that beta of 24 degrees, if alpha is actually 108.4 degrees, then the gamma is going to be 180 degrees minus the 24 and minus the 108.4 degrees, giving us instead that gamma is 47.6 degrees. Now, based on these 2 gammas, you find the C. Okay? The way you go about finding the C, go back to the original side angle pair, sine of 24 degrees over 3, and compare that now to the gamma of 84.4 degrees, the sine of 84.4 degrees over C, and solve that for C. That's going to be C is 3 times the sine of 84.4 degrees divided by the sine of 24 degrees. 3 times the sine of 84.4 degrees divided by the sine of 24 degrees, and I get 7.34, so I'll just go ahead and round that. There's a second solution, of course, because if gamma had instead been 47.6 degrees, then you would have compared the original side angle pair to that angle gamma of 47.6 degrees. And solving there for C, 3 times the sine of 47.6 degrees over the sine of 24 degrees. In this case, what do we get? 3 sine of 47.6 degrees divided by the sine of 24 degrees gives me 5.446. So I can round that to 5.4. And this is your example then of when you get two solutions to a triangle using the law of sines. Okay? All right, let's try to find the area of a triangle. Let's try problem number 28. We're asked to find the area of the triangle with the given measures. They tell us that side B is 11, side C is 8, and angle alpha is 28 degrees. Okay, let's draw what we have here. 28 degrees. I'll put alpha here, so that's side A. And that means that side B could be here, and side C could be here. It doesn't really matter which one's which, right? Now think about how you go about finding the area of a triangle. Area of a triangle is 1/2 times the base times the height. Well, I can certainly take this 11 to be the base. Just orient your triangle so that that's the base. The height of it is this right here. So now 1/2 times 11 times the height, and the big question is, how do I find that height? Well, as you drop straight down to consider the height, you are in fact making a right triangle, aren't you? You want to find the opposite side of this right triangle given this angle and the hypotenuse of 8. The sine function will do that for you. The sine of 28 degrees is the height divided by the hypotenuse of 8. Opposite over hypotenuse. Therefore, the height of your triangle is 8 times the sine of 28 degrees. 8 times the sine of 28 degrees gives me 3.756. That's what I put here. And now I'm all set to calculate that. 3.756 times 11 times 0.5 for a half, and we get 20.66 square units. Whatever the units were here, square units here. Okay. All right, so basically that's it to solving a right triangle using the law of sines. It's quite a simple process, actually. In the next section, we'll be looking at a related concept called the law of cosines, and we'll see how we use that to solve a right triangle as well. As always, if you have questions or concerns, please do not hesitate to contact me. Shoot me an email, let me know what's going on.